Okay, what I'd like to do is run through a little demonstration on how to use Matlab to take a Laplace transform and an inverse Laplace transform. Now, we'll say there are some circumstances under which Matlab doesn't quite interpret the Laplace transform to be the same. So, especially when you come to properties and you have to have things like time shifts and time shifted step functions and things like that, MATLAB is going to be a little awkward in how it interprets that. What MATLAB does understand is MATLAB does understand that the Laplace transform is defined as a single-sided transform only. So, for example, if you try to take the Laplace transform of cosine of 2 omega t, or cosine of 2t, then it's going to do that, but it is going to assume the function begins at t equals 0 and is initialized there. So that part is built into MATLAB and how it does the Laplace transform. So the first thing that you have to do is the Laplace transform, like a lot of mathematical operations in MATLAB, is if you want to actually type in an equation in terms of t, you don't want to define t as a matrix, so you don't want it assigned. In other words, t has to be a variable, and so the way to make t a variable is to use the symbolic math toolbox. The symbolic math toolbox has a command in it called sims that allows you to construct, to basically identify variables that will be symbolic variables. And there's lots of potential syntax here, but in this case, it's just going to be very simple what we need to do. We're just going to say we're going to define some symbolic variables, and the variables are going to be t, time, f, function of time, s, the Laplace variable, and big F, function of s. So we're just going to define those, and a lot of times it takes MATLAB a second to do that. I had actually previously defined those symbolic variables and had to throw that lecture away because it had some errors in it. So they're already here on the workspace, but had they not been here, once I do the symbolic variable definition, it would have defined them. All right, and now what you do is you just define a function. So you can say f is 3t, and you have to enter it with appropriate syntax. So you have to use your multiplication. So we'll say 3t cosine of, let's do 2 times t. Okay. And then I always leave the echo on and don't put the semicolon when I'm using symbolic math, so that it feeds it back to me so that I typed in what I thought I typed in. Okay, and then now all you have to do is you just use your one of your other defined symbolic variables, and we're going to say big F is the Laplace of little f. And so there you go. So this is, you kind of got to read the syntax, which is not always super easy. It looks like it's 6s squared divided by s squared plus 4 quantity squared minus 3 divided by s squared plus 4. So as you can see, it does take the Laplace transform. And like I said, it can sometimes be a little hard to read when you're trying to read, because it's typing it all out on one line. It's not giving you that nice fraction, but it will take the Laplace transform. It'll do it pretty well. Now, the step function in Laplace, in MATLAB, is called the heavy side. Let me do a help. Heavy side. That's kind of a physics word. So heavy side is the step function. Heavy side of x is basically 0 for x equal 1, and 1 for x 0 for x less than 0, and 1 for x greater than 0. They do assign it at 0 a value of 0.5. That's because in computational methods, Matlab or whatever, you can't have an undefined point. So as you know, in mathematical analysis, theoretically there's a jump from 0 to 1 at 0. You can't really have that in computational systems, so we define it as 0.5. And in fact, in mathematical algorithms, it's often defined as 0.5 also. It can be changed to any value by the call symbolic heavy-sided origin, comma, v. And that would be basically, if you don't set it to be 0.5, if you set it to be 2, then basically that's like saying your step function's going to have a magnitude of 4. So if your step function has a magnitude, you can either say 4 times heavy side of x, or you can set this value v to be something different. Okay, so there's also the Dirac. That's the delta function or the impulse function. So you have an impulse function in MATLAB as well. So we could say, for example, f is Dirac of t. Okay, and then we could do a f is Laplace of f again. And it'll feed you back that that's 1. We can say f is heavy side of t. And then we can do Laplace of f again, and it'll give us our 1 over s. Let's see. I trying to remember if you can time shift the step function. So let's just do it. I don't remember if you can do it or not. So we'll do f is heavy side of t minus 2. I don't know if it'll do this because t is a symbol and 2 is a number, and for whatever reason, well, we'll see. Okay, and then let's take that Laplace. And yeah, there you go. So here's your exp to the minus 2s divided by s. So now let's look at the inverse Laplace. So for the inverse Laplace, you use the term I Laplace. Okay, and basically that will take the inverse Laplace transform. Once again, the variables are going to have to be independent variables. Matlab defaults to understanding s as the Laplace variable, and so you noticed when we took the Laplace transform, yes, we had defined s as a symbol. Even if we hadn't done that, it still would have given us this in terms of s. So even if I didn't have t defined as a symbol, when I enter a function of s and ask it to take the inverse Laplace, MATLAB defaults to t. So MATLAB was actually designed and created around control theory initially, many years ago. And so it's got a very good understanding of Laplace analysis and a lot of good defaults to what the variables should be. Okay, so let's just type in a function. We'll let f be s divided by s plus 5. Okay, and then we'll just do I Laplace, and you can either tell it to make little f equal to I Laplace, or you don't have to give it a variable name. It'll just give you the output in that case. Okay, and you see it gives us that would be the impulse function minus 5e to the minus 5t. So it'll do Laplace of pretty complicated fractions. So, for example, if I wanted to make this more elaborate, I could even do a cube plus 5s plus 1. So I could even do, a polynomial in the denominator. And then I could take the inverse Laplace. And you can see it'll give me the result. Now, so you notice that it's got some odd things here as far as the output goes. And that's part of the issue with taking an inverse Laplace in Matlab, is you have to be able to understand what it's actually telling you. So symbolic summation just evaluates the sum of a series, and so it's their mathematical term implicating summation. So it's really hard to interpret their output here, which is why when you get to a certain level of complication on your Laplace transform and inverse transform, especially on your inverse transform, I always recommend that rather than using the iLaplace with the symbolic math, you first of all have Matlab do for you a partial fraction expansion. And then once you've done your partial fraction expansion, you can then take the inverse transform term by term, or by the time you do a partial fraction expansion, it's often pretty obvious what the inverse transform is going to be. So that's the only caveat with using Matlab to take the inverse transform particularly, is that sometimes you do get terminology that is hard to interpret the output that Matlab's actually trying to give you. Okay, well, I'm going to close this video here because that pretty much sums up the syntax for the Laplace transform and the inverse transform. The next Matlab video that we'll do will illustrate how to find the roots of a denominator, how to do a partial fraction expansion, and then sort of how to put that together with utilizing the tables to take an inverse transform.